This demo focuses on the use case 1 scenario to showcase the advantages of using the VO stack in complex robotic software implementations in emergency and disaster scenarios. More specifically, it shows a navigation and mapping solution in an unknown environment. The application graph includes multiple components being deployed as containers in a Kubernetes cluster. The VO container is at the core of the demonstration as a virtual abstraction of a complex physical robot, enabling flexibility and interoperability with other application components. The communication from the VO to the physical robot exploits the VO southbound interface, implementing an MQTT protocol. The northbound interface instead enables an HTTP communication towards the graphical user interface container. To start with, we deploy all required containers and services on the Kubernetes cluster on our cloud infrastructure. This includes the web application to interact with the VO and in a Foxglove dashboard to display the robotic messages and data. On the physical robot, we run a container hosting the VO Web of Things runtime environment to expose the properties and implement the software behind the actions triggered through the VO. It also starts the MQTT connection to the MQTT broker for communication with the VO. Using the web application, we can interact with the robot device through the VO abstraction. The thing descriptor for the robot exposes actions to start processes on the device. It also exposes properties that can be fetched over the VO. For instance, the battery level and its charging status. At the beginning, no data is available since the processes did not yet start on the physical device. To do so, we trigger an action to launch a robotic ROS process on the device that brings up all robotic controllers and the basic scripts. After the process started, we can see in our Foxglove dashboard container the ROS topics being displayed. Here we see, among others, the camera stream, the LiDAR information, and the virtual representation of the robot in the dashboard. We now also can read the battery status and charging level now by reading the exposed properties or through the VO periodic function. We can interact with the robot using the Foxglove dashboard to navigate the environment. Here you see the commands being sent from the dashboard to the robot, the physical robot moving, and the information being updated in the dashboard. To perform the mapping, we need to trigger another action on the robot through the VO. This will start a ROS mapping process on the device after verifying there is a sufficient level of energy in the battery. By controlling the robot through the dashboard, we are now building a map of an unknown environment. We can now save a built map using another action through the VO. The saved map will be on the physical device, but will also be exposed for access through the VO. The map can be retrieved using an action so that the map can be displayed in the web application for further use in the disaster scenario. For instance, non-robotic experts and other first responders teams can access the map for an enhanced situational awareness.
Now we move to the network and device monitoring application. The wireless sensor nodes and robots exploring the region are continuously monitored to prevent risks of device and network disconnection. To this aim, networking and device information are sent to the application components monitoring the network status. In this demo, we suppose that the wireless sensor network is sending data to its gateway. We want to visualize the collected data in the graphical user interface. In the full application graph, Node 4 represents our graphical user interface. 2VO are communicating with it via HTTP. VO1 represents a ground robot, whereas VO2 represents the wireless sensor network gateway. In the rest, we focus on the VO stack implementation of the gateway. A Raspberry Pi 3B has been used as the wireless sensor network gateway. It runs a WAT runtime to communicate via CoAP with VO2. VO2 and the web application are hosted each on a computer. For the moment, the Raspberry Pi as well as the two computers are in the same local area network. First, we run the program on the Raspberry Pi using VO WAT. The Raspberry Pi is now listening on the CoAP port and generating dummy data. Its thing description is ready to be consumed. Now, we run the program on the computer hosting V02 using also V01. As defined in its YAML file, V02 consumes the exposed thing on the wireless sensor network gateway. It also runs a user-defined periodic function to read data, as well as generic functions to print its status and the status of the device it is consuming. Using CoAP protocol, it then starts periodically reading the dummy data generated by the wireless sensor network gateway. Finally, we can visualize the generated data on the web application. As shown in this demo, we can have a tab for each application in our use case. In the Network Monitoring tab, we can create a dashboard showing the status of the devices and the network. Information such as battery level, connectivity, congestion, and sensor nodes positions can be visualized. In this demo, the generated dummy data by the wireless sensor gateway is sent to the web application via its VO. The plots update automatically with new readings.